Hey guys, it's Margot at Lanterna here, back with another analysis and approaches online maths video. Today looking at integration part 3, moving on from last time where we looked at integration by substitution. Today we're going to be covering the rest of section 5.16 of the higher level syllabus and looking at integration by parts. Again, an incredibly powerful method of integration. I hope you find this video really useful and I hope you enjoy it. Okay, so integration by parts then. This formula right here, I've copied and pasted directly from the formula booklet, so there shouldn't be any differences. So let's have a think about when do we apply integration by parts. If just as a recap, in the last video we looked at integration by substitution, and we saw that integration by substitution was a really powerful method when we had the integral of a function of some other function g times the derivative of that function g. And we got a really powerful method to solve integrals in that form. Now, through integration by parts, we apply integration by parts when we have the integral of a function times the derivative of some other function, such that it can be simplified if we integrate one of the functions, v, and we differentiate the other function, because essentially we're converting from one integral to another. So the only way in which that's really useful is if this second integral is simpler than the first one, i.e. one which we can solve using those integrals in our formula booklet. Now, the question we're really asking ourselves here is when we see an integral like this is which function should we differentiate to simplify the integral? And this function we should label as u. Now, this question is often more relevant and gives you more information than asking yourself which function should we integrate to simplify the integral. So we're going to ask ourselves this question right here when we look at some examples. So let's look at this first example. We've got the integral of x times e of x. So, we see, okay, we've got two functions, right? We've got x and e of x. So one of these functions is going to be the one which we integrate, and the other is going to be the one that we differentiate to form our new integral. Okay, so we'll ask ourselves, which function should we differentiate to simplify the integral? Well, let's take u is equal to e of x. First of all, well, if we find the derivative of u being e of x, the derivative of that is just e of x, right? So that would give us an integral which would look something like, well, the integral of our other term x times the derivative of our second term, so x squared over 2 times e of x. Well, that's not any simpler, arguably more complicated than the integral we started with, right? So we do not want to choose u being e of x to differentiate e of x and integrate x. Let's try instead to do it the other way around. Let's choose u is equal to x, which means we differentiate x and we integrate e of x. Well, that would give us an integral which looked something like, okay, the derivative of x, which is just 1, times by the integral of e of x, which is just e of x, so we get e of x dx. Okay, well, we know what the integral of e of x dx is, right? We can take it straight from our formula booklet. It's just e of x. So this is exactly the path we want to follow. We want to choose u to be equal to x, and we want to choose dv by dx to be equal to e of x. So let's have a look at the full solution then. We said we want to choose u is equal to x, and we said we wanted to choose dv to be equal to e of x dx, or dv by dx is e of x, it doesn't matter. Okay, we see that then if we want to use this formula right here, okay, well, we're going to have a du by dx, so let's find that first of all. We say that du is equal, du by dx is equal to 1, and we want to find v, which is the integral of dv, right? If we take the integral of both sides, we find that v is equal to e of x. That's just from our formula booklet. Substituting all these values in then, well, then we see that x times e of x dx is equal to u times v, so x times e of x minus the integral of v, which is e of x, times du by dx, which is 1 times dx. Well, we see x times e of x, we know what the integral of e of x is, it's just e of x. And then finally, because it's an indefinite integral, we just have to add our constant of integration to the n. So there we have it. This is our first example for integration by parts. So let's have a look at another example. X cubed times ln of x dx. So we need to think about, okay, first of all, what is the integral and derivative of each of these functions? And then let's see which combination is most useful to form a new integral. Okay, well, we know that the integral of x cubed is x4/4, and the derivative is 3x squared. Well, ln of x, okay, we don't actually know the integral of ln of x, or at least it's not given in our formula booklet, which is a clue that we shouldn't be using ln of x as the function which we should integrate. So in that case, taking that hint that we don't actually know explicitly what the integral of ln of x is, let's take ln of x then as the function that we differentiate. Well, if we take ln of x as the function which we differentiate, then we'll get an integral which is going to look something like the well, integrating x cubed would be x4/4 times by the derivative of u, which is 1/x. Okay, well, that's a really nice integral, right? That's just the integral of x to the power of n with some constant. We know how to solve that. Okay, so we've established that we want to take u is equal to ln of x, because that gives us the integral, which is easy to solve using the formulas in our formula booklet. So let's have a look at the full solution again then. So we decided that u is equal to ln of x, and therefore that leaves us with dv being equal to x cubed dx, taking then the derivative of u with respect to x. This is equal to 1/x just from our formula booklet, and then finding v by integrating both sides of that equation. We find that v is equal to x to the 4/4. Again, that is in our formula booklet. So if we put this together, then this is equal, or the integral of x cubed ln of x is equal to u times v, which is ln of x, times by x to the 4/4. Now that's not particularly nice, but that's fine because we don't need to integrate it, minus the integral of v times by the derivative of u, which is 1/x dx. So let's simplify that integral a little bit. Minus the integral, well, this is going to be x cubed over 4 dx. So we find finally solving that integral, just using the integral of x to the n from our formula booklet, that this is equal to 1 minus, well, taking out the factor of 1/4 at the front, integrating x cubed to get this as our final solution. So if I write that out a little bit more simply, we can say, okay, so that was another example done right there. So we're really getting used to asking the right questions to find which function to integrate, which function to differentiate. Okay, let's have a look at this example then. So this is kind of similar to our first question. We have where we had x times e of x, we now have x squared times e to the minus of x. Okay, so maybe pause the video here and think, okay, what would I choose as u and what would I choose as dv by dx? Well, we see that here, again, if we were to choose u to be e to the minus x, the derivative of that is just going to be negative of e to the minus x. And we'd have to multiply by that by the integral of x squared, which is x cubed over 3, which really doesn't help us at all, right? The integral of e of x times x cubed. So let's choose again, u is equal to the x term, x squared. Then in that case, we have the derivative of that, which is 2x times the integral of e to the minus x, which is minus e to the minus x dx. Okay, well, this still isn't entirely useful to us, but let's just kind of write this out a little bit more neatly. We see that this is equal to the integral of x times e to the minus x dx. Now, this is where we notice something, and we should notice that this right here is actually incredibly similar to what we solved in part 1. So the idea here is that we're going to have to apply integration by parts twice, right? Because we can't quite yet solve this integral very easily, but we saw that from part one, if we apply integration by parts again to that, we should get to an integral which we can solve. So let's have a look at the solution for this then. So we established that we want to choose u equal to x squared, because that's going to simplify the integral, and dv is equal to e to the minus x. So then du is equal to 2x, and v, again taking the integral of both sides, is minus e to the minus x. Okay, so let's take the first step then. It's our integral is equal to u times v, which is x squared times minus e to the x, minus the integral of v times du by dx, so negative of e to the minus x times by 2x dx. Okay, let's simplify this a little bit. Minus x squared e to the minus x plus 2, I'm taking out that factor of the minus sign, x times e to the minus x dx. Okay, so we said here that if we apply integration by parts to this part, we can actually find that integral. So we see this is very similar to that case we solved in the first example, right? So we should be able to identify that u here, I'm going to call it u prime because we've already used u for the first integration by parts right here, and I wouldn't want to confuse the examiner. So we're going to say u prime is equal to x, and we'll say dv prime is equal to e to the minus x dx. So maybe pause the video right here to work out that second integral using integration by parts. I'm not going to do the full working now, but what we should find is that that integral, so just the integral, I'm ignoring that coefficient of 2 for now, is equal to minus x to the e to the minus x minus e to the minus x. So that's what we should get for that second integral. So if we're going to plug everything in, well, we still have that first term minus x squared e to the minus x, and then we have plus 2 times, well, all of this, right? That's what came from the integral. So plus 2 times minus x e to the minus x minus e of minus x, and remembering finally our constant of integration c, because it is an indefinite integral. So, you know, it doesn't look particularly nice, it's a little bit messy, but it doesn't matter, right? We've solved the integral of what was initially a really difficult integral to solve. So all we do here is expand out those brackets, and that would give us our solution. Perfect. Okay. So that was a slightly trickier example because we had to use integration by parts twice. That's not at all uncommon for the IB to ask you. So keep that in mind, that that could potentially be something that you could get asked. Now we're going to look at another integral. So this is an interesting example. It's, again, a little bit more tricky than the previous ones. It requires some kind of additional thinking behind it. And this is an integral which could be asked on your exam paper, but that is the IB assuming that you've seen how to solve an integral like this before. So pay particularly close attention to this one because it uses a small trick which the other ones don't. So we see straight away, right? This is an integral of ln of x. Okay, well that's different to our last examples because we very clearly had in our previous examples two functions, right? We could identify a u and a dv by dx, whereas here we only have one function. So how do we deal with that? Well, also let's just remind ourselves, ln of x, we don't know what the integral of that is, right? So that straight away tells us that that is going to be our u and that is going to be the function that we differentiate. The way to get over, the trick we use to get over the fact that this is the integral of one function is we say that this is the integral of 1 times by ln of x. So we can now see So we can now see, okay, we have two functions, right? We have a function which is just 1, a constant, and a function ln of x. Okay, so we said, well, we don't know how to integrate ln of x, so there's no way we're choosing that as our dv by dx. We're going to say u is equal to ln of x, and that only leaves us with dv is equal to 1 times dx, right? du by dx, we know from our formula booklet, this is equal to 1 over x, and integrating dx leaves us just with x. So if we plug all these numbers in our formula, we find that the integral of ln of x dx is equal to u times v, so x times ln of x, minus the integral of x times 1 over x dx. And look at that, that is an integral which is very simple to solve, right? X times 1 over x is just 1, so we're just integrating the integral of dx minus integral of dx. So overall we find this is x ln of x minus x, and then our integration constant plus c at the end. So we've solved this integral where we struggled with initially the fact there's only one function, and how did we solve that? Well, we multiplied it by 1, and we chose 1 to be the function we integrate and ln of x to be the one we differentiate. So a really important example right here. Okay, so for integration by parts, we just looked at loads of examples, and I've tried to convey, you know, the way of thinking about these problems, which is really important when we approach these. I hope you enjoyed that video. I hope you found it useful. It's a tricky topic, so go away and do lots of practice. For now, check out our other videos on our website or online in subjects like ESS or economics, biology, chemistry, you name it. I hope you enjoy this, and I hope to see you again soon.